All right, 15.3 area by double integration. This is going to be a very quick video. I'm going to combine two concepts into one. Uh, and yeah, that's pretty much it. They're two formulas. I'm going to do a problem on each formula and then we're going to be done. It's really quick. So let's talk about the first formula. You have an area of a region, all right, is given by the double integral of dA. Over the region. So what does that really mean? It means that if you have some region R, right? Let's use a different color. Yada da da. So if that's like R, right, then the area is just the double integral, and then one, right? Because dA is really just one times dA, but you never write the one. Dx dy or dy dx. So again, I had an entire video that pretty much we talked about which one you use, but dA is just dy dx or dx dy. Yeah, so you do this integral, right? So if you look at problem 15, 3.4, okay. Yeah, so it says sketch the region bounded by the given lines and then evaluate the region's area as a iterated double integral and evaluate the integral. So this is a lot like what we did earlier in the 15.2 video if you watched it. Okay, so the parabola so you got the parabola x is equal to y minus y squared, and you got the line y is equal to negative x. All right. And okay, so the first thing is sketch the region. So y is equal to negative x is going to be this line right here. Oh my god, go through the origin, please. I can't draw, but okay, something like that. That looks disconnected. Oh boy. Oh, better. Okay, so this is y is equal to negative x, right? And then now you got x is equal to y minus y squared. Oh, what does that look like? So here you just want to plug in points, right? X is equal to y minus y squared. So if y is equal to 0, x is equal to 0, right? So x is equal to y minus y squared. So here's this. If y is 0 is x is 0. If y is equal to negative 1, x is equal to negative 2. And if y is equal to positive 1, x is 0. Okay, and then if y is 2, x is negative 2. All right, so it looks something then like this. So if that's 1 and that's 2, then it's 0 here, it's 0 here. It's a parabola that opens up this way. And then, yeah, so at 2, it's going to be at negative 2. And so we go like that. All right, and this point is 2, negative 2, or negative 2, comma 2. What am I doing? And it's on both lines. It's on y equals negative x, and it's on the parabola x is equal to y minus y squared. All right. Now we need to set up an iterated integral over this region that calculates the area. So that's going to be the double integral. Area, again, is equal to the double integral of dy dx or dx dy. Let's do dx dy in this case, right? Because if we look at our x number of equations, I got x is equal to negative y, that coming from y is equal to negative x, and then right, and then I have x is equal to y minus y squared. So I have two equations for x. But if I do y, right, I got y is equal to negative x. But when I try to solve this guy for y, that's a huge pain in the ass, right? Yeah, I'm not even sure how what you would use for y there. Yeah, so okay, so y is equal to negative x, and then something for the parabola, right? So yeah, obviously we don't want to do dy dx, so we want to do dx dy first since we have two equations for x. Then they'll fit in the bounds nicely, x equals, and all right, so dx means I draw a line like this. There's dx, and it hits the straight line and then the parabola. So my lower bound is going to be x is equal to negative y, and then my upper bound is going to be y minus y squared. Okay? And then dy then, what's the smallest value for y? Well, that's going to be 0. And then the biggest value for y is going to be 2. Right? And so how do you find that? Well, one way you can find that is you can set these guys equal to each other. So you have negative y is equal to y minus y squared, and then you get 2y minus y squared is equal to 0, and then you get y is equal to 0 and 2. So that's how you find it, and that's how I get the bounds here. Okay, so now there's my bounds, dx dy, that gives me the area, right? There's technically a 1 in here. So what happens when I integrate? I get 0 to 2, y minus y squared minus a negative y dy. So that's what I'm going to get. So if you do the integration out, that's what you get. And then you get 0 to 2, 2y minus y squared dy. That's equal to y squared minus y cubed over 3, evaluated from 0 to 2. And you get 4 minus 8 thirds, or you get, which is 4 thirds, is going to be your answer. Okay? Cool. So that's how you do the area thingy, right? So that's how you set up an integral for the area, which I already emphasized a lot in 15.2. But here's another example where you actually do the integral out. So another good example using that formula. The 2 then is the average value of a function over a region, and it's 1 over the area of the region times the integral of the function. So let's say the function is f of xy evaluated over the region. Okay, so that makes sense, right? You integrate the function over that region, and then you divide it by the area of the region, and you should get the average value. So for example, f of x comma y is equal to sine x plus y, and then let's say the region R is a rectangle, 0x pi, and then 0y pi over 2. Okay. So yeah, so if that's pi, then this is pi over 2, and then it's this region right here. So the area is going to be, right, it's a rectangle, so it's pi times pi over 2, which is pi squared over 2. Okay, and then the average value of the function is going to be 1 divided by pi squared over 2 times the iterated integral, so the double integral of f of xy, which is sine x plus y, and then here, dy dx dy doesn't really matter because you have a rectangular region, okay? And we're just going to do dy dx. And no particular reason why, besides that's just the way I wrote it down on my sheet of paper. So that's going to be the average value of the function. So this is really 2 over pi squared out in front, okay? If you take the integral of the first guy, now you got 0 to pi. This becomes negative cosine x plus y evaluated from 0 to pi over 2 dx, right? And that's equal to then 2 over pi squared, 0 to pi, and then this becomes, this is actually interesting, it's negative cosine x plus pi over 2 plus cosine of x plus 0, right? Because it's minus a negative. Okay, because that's how we evaluate the integral, right? And then it becomes a plus sign. So that's actually equal to 2 over pi squared, all right? So let's just write this as plus. Saves us some parentheses as well. And that was just showing us how big why that was a plus. And now we've got to integrate this guy again with respect to dx. So now I get 2 pi squared times, and then here you get negative sine x plus pi over 2 evaluated from 0 to pi, and then you get plus sine of x, right? X plus 0 is just x, evaluated from 0 to pi. Okay. And what do I get? Well, I get 2 over pi squared. This guy is 0, right? Because sine at pi is 0, sine at 0 is 0. And now I get negative sine at 3 pi over 2 minus a negative sine at pi over 2. And what is that? That is equal to 2 over pi squared times sine of 3 pi over 2 is 1. So this becomes, sine of 3 pi over 2 is negative 1. And you got a negative sign out here. So that's becomes positive 1. And then this is positive 1 plus sine of pi over 2, which is 1. And so our average value of our function, sine of x plus y, over the region given to us up there, is going to be 4 divided by pi squared. Okay, so that's how you find the average value of a function over a region. Fairly simple. Sometimes you might have to actually do an integral to find this area. Right here we have rectangle, which is why it's really easy to find the area. So that's about the only variation I can think of on this problem. So that's it for 15.3. Really quick section. Only this one video is needed. 15.4, we're bringing back the polar coordinates, and we're going to be integrating over polar coordinates. It's going to be interesting. It's going to be very useful, and it's going to be something that you're going to use a lot as well in this in this course for the rest of the course. And hopefully this video made sense, and I'll see you guys in chapter 15.4.